So let me consider you have a cantilever beam like this. Okay, so one end is fixed, the other end is free, and you have a force. Let me consider you have a force of around 500 Newton, which is acting in this beam. Okay, and they mentioned what is the cross section area. So cross section area, let me consider it is 1000 mm square, and your Young's modulus is again same 2 into 10 power 5 Newton per mm square. Right. So let me consider this beam as a length of around 500 mm. Right. The beam is having a length of around 500 mm. So this is the overall distance of the beam. Right. So length is also given. So usually, so you can able to see that it's axial loading which is acting like this. So how you solve this by using strength of material? So we have a common formula. What we say, we have del L. So we understand del L is equal to PL by AE. So this is the formula we usually use, right? Where P is the force, L is the length of the beam, bar, A is the cross-section area, and E is your Young's modulus. So if I substitute, I will identify what is the total change in length, right? Let me substitute it. So if I have here, so 500 into, so L is again 500 divided by A. Here is 1000 into E. So E is 2 into 10 to 5. So how much you will get? Okay, so what I am getting is 0.00125, right? So this is in mm. So this is the value, right? So this is our usual method. So whatever we use strength of material approach, we use to solve it. Now let us solve this particular problem by our usual procedures. So point collocation, subdomain collocation, and all these things. Let us solve the same problem, right? For this, first I need this differential equation, right? It's a bar problem. For the bar problem, we already derived a differential equation. What will be the equation? The equation will be AE d square u by dx square plus some qx. There will be the equation what we derived is plus qx, where q is the uniformly load. So uniformly varying load. So there will be some UDL something here. So which will be acting continuously, or we can also say it as a self weight. Okay. So but here we are not mentioned any self weight here. So there is no plus q. So this is 0, right? Is equal to 0. So this is my differential equation for this particular beam, right? So AE d square u by dx square is equal to 0, right? That is my differential equation. Okay. So what is the boundary conditions? So I need some boundary conditions, right? So in order to solve this. So when you look here, my x is here, which is 0 when I start at this location. At this location, my x is 500 mm, like this 500 mm. Okay. So when I say a boundary condition, I can say that when x is equal to 0, when x is equal to 0, what about your deflection? Del is your deflection. According to this, del is your deflection u of x. So what is your deflection here? So your reflection u will be equal to 0 because that is a fixed in, right? The other part, you have a point load. What we have is a point load, right? So, but there is a deflection here, so which we can't apply it. So what we understand is, so I can't put when x is equal to 500, u is equal to 0 because that is a free end which will have a deflection. Okay, that is what we are planning to identify. Okay, so in that case, in order to apply other boundary condition, I am shifting this u in terms of force, right? So when I shift it, what will get my force? I can write it as force. I can write it as AE du by dx. I think this also we discussed. Okay, so we know that your force is stress into area. Your stress is, what is your stress? Again, I can rewrite it. Stress is Young's modulus into strain. Okay, so into area. So again, when I redo this, so this strain I can write as du by dx, which means I will get AE du by dx. Right. So this is how I got this force as AE du by dx. So when x is equal to 500 mm, I have this AE du by dx. AE by du by dx is not equal to 0, but I have a value. So what is my force? My force is 500 Newton. So AE du by dx is 500 Newton. Okay, this is my boundary condition. But let me concentrate only on du by dx. So not this AE, right? So I am bringing on the other side. So what I will do, I will write it like this: du by dx is equal to 500 divided by AE, which means your du by dx will be equal to, so you know it is 500, sorry, 500 divided by A is 1000, E is 2 into 10 power 5. Let me substitute these things, right? So when I substitute these things, my second boundary condition, when x is equal to 500, your du by dx will be equal to, so whatever the value I am getting, so you are getting 500 divided by the remaining terms, 2.5 into 10 power minus 6. This is my value. So now I got these two boundary conditions. So I got the differential equation, I got the boundary conditions. So both are completed, right? So the next step is I have to proceed our usual method. So what I do, I have to take up trial function. So let me consider what is my trial function. So trial function u of x is equal to a naught plus a1x plus a2x square. So something like this. Okay, I'm not going beyond this because you know that it will be a complicated one, right? So this is a simple problem. I'm going to take only one constant. Make sure I have only one constant. So why I go up to x square? If you look here, I have gone up to x square. What is the reason? Because our equation, differential equation is d square. Okay, which means if I differentiate this, sorry, if I integrate this twice, sorry, this u I have to differentiate twice, right? If I differentiate this u twice, x square will be around x, it will be a constant, it will be 1. So when you differentiate, so you have only one constant. That is the reason I am taking up to x square, right? Okay, now let us take. So what I do, I have to first substitute my boundary conditions. I have to satisfy the boundary conditions. What is my boundary condition? When x is equal to 0, u is equal to 0. If I apply in this, so x is 0, u is 0. So I'll get a naught is equal to 0. So it satisfies something like this. So that is over. Second boundary condition. When x is equal to 500, when x is equal to 500, du by dx is what we get, which is 2.5 into 10 power minus 6. Right? This is my second boundary conditions. So I'm going to apply this one. To apply this, first I have to differentiate this, right? So I got u is equal to a naught is gone. So because it is 0. So u is I'm getting a1x plus a2x square. So differentiate this once, you'll get du by dx, which is equal to a1 plus 2a2x. So this is my term. Okay. So in this, I have to substitute this, right? When x is equal to 500, du by dx is 2.5 into 10 power minus 6. So when I substitute here, so 2.5 into 10 power minus 6 is equal to a1 plus 2a2 into 500. Okay. So what I will get? I'll get some equation. So I want to replace this a1. So I will get a1 is equal to 2.5 into 10 power minus 6 minus, so they are remaining term. So 500 into 2, so it is 1000 a2. Okay, this is my a1. Okay, so now I can apply this in my trial function, right? Let me apply in this trial function. What is my new trial function? So my new trial function is u of x is equal to a naught is 0, a1 is this, so 2.5 into 10 power minus 6 minus 1000 a2 into x. Okay, so a1 x. A1 is what I substituted there. So remaining is a2, right? So plus a2 x square. So this is my trial function. So now I achieved what is my trial function. This trial function I have to substitute in this differential equation, right? It is d square u by dx square. In that case, I have to differentiate this twice. Okay, so let me consider du by dx. When I put du by dx, so you will get this entire term. Okay, x I am putting hyphen because no need to write it. Again, when I do that, it will become 0. So that's why I am eliminating that step. So x, when I differentiate, you will get 1, right? Plus this one 2a2x. This what, so x square, when I differentiate, I'll get 2x, right? So again, when I differentiate this, d square u by dx square, what happens? This becomes 0. So this will become 2a2. So I get only 2a2. So this I have to substitute in my differential equation. What is my differential equation? My differential equation is a e d square u by dx square, which is 2a a2, is not equal to 0. Because when I substitute it, I will say that it is not equal to 0. So I will call this as r of x. Okay. My aim is to identify what is this a2 value. So once you achieve this a2 value, then I can able to say that that will be your solution. Okay. So now I got what is my r of x, residual. My residual is 2ae a2. This is my residual. Okay, there is a common residual which we are going to use for all the methods. Okay, so now we'll go for point collocation. First one, point collocation. So according to this method, my boundary, it starts from 0 and goes up to 500, right? So my cantilever beam, it is not a beam actually, cantilever bar. So it's starting from 0 and it's the length is having up to 500. So if I consider R of x, you have only one unknown. So how many unknowns is here? Only one unknown is here, which means I have to take only one point in between these two, right? So one point will be 250, middle point. Okay, so what I can do, I will put R of 250 is equal to 0. So instead of x, I have to put 250. So you don't have x here, right? Which means I will directly write 2ae a2 is equal to 0. Right? So there is no other term, which means I can say that a2 is 0. Okay. So what I achieve is my a2 is 0. Right? So now what I'll do, I use my trial function. This is my trial function, right? I'm going to substitute a2 as 0 in my trial function. That will be my answer. So here substitute a2 is equal to 0. So what will get? I'll get u is equal to, right? A2 is 0. So we'll get 2.5 into 10 power minus 6 x. Okay, this x. A2 is 0. This becomes 0. So this term goes 0. So remaining, what? This is my u of x. This is my u of x. Right? So we already identified in Santha material. So what we identified? We identified that at this location, at x is equal to 500 mm, my deflection is 0.00125 mm. Okay, so PL by after by applying PL by E. So here, let me check it out. What will get? So I have to substitute U at 500. U at 500, which is equal to 2.5 into 10 power minus 6. X is 500 now. So into 500. So multiply with 500. So what you're getting? So 0.1 into 10 power minus 3. Okay. So which is similar to our previous value. You can see that there is a little bit error. Okay, so there is a little bit error here, right? So what I achieve here is 0.0011. So whereas the real solution is 0.00125. Okay, a small error is here. Okay, this is what the point collocation. So it is an approximate method. Okay, right. So let me proceed with the same for other methods also.
சார் அந்த ஆர் ஆஃப் எக்ஸ் வந்து ஜீரோன்னு ஆர் ஆஃப் அட் 250 ஜீரோன்னு போட்டிங்க சார் அது மட்டும் எப்படி சார்
இந்த பாயிண்ட் கலெக்ஷன் மெத்தட் என்னன்னா நம்ம இந்த ரெசிடுவல் ஜீரோ கொண்டு வரணும், ரைட்? இந்த ரெசிடுவலை எப்படியாவது நம்ம ஜீரோ கொண்டு வர்றது தான் இந்த பாயிண்ட் கொலோகேஷன் மெத்தடோட மெயின் எய்ம். ஸோ இந்த ரெசிடுவலை நான் எப்படி ஜீரோன்னு சொல்றேன்னா, ஸோ இந்த எத்தனை அன்னோன் பார்க்குறோம், இந்த அன்னோன்ல ஏதாவது ஒரு வேல்யூ இந்த ஜீரோல இருந்து 500 வரைக்கும் லென்த் இருக்கு. ஒரு பர்டிகுலர் வேல்யூல வந்து நம்ம ஆர் ஆஃப் எக்ஸ் ஜீரோன்னு சொல்றோம். ஓகே, இது ஃபார்முலா படி வச்சுக்கோங்க. இது வந்து ஆர் ஆஃப் எக்ஸ் ஜீரோனா ஆர் ஆஃப் எக்ஸ் 250 is equal to 0 அப்படின்னு எடுத்துக்கிறோம். புரியுதுங்களா?
ஓகே சார். அப்போ நம்ம அங்கேயே மேலே ஏஇ 2 ஆஃப் ஏ 2 இஸ் நாட் ஈக்குவல் டு 0ன்னு போட்டீங்களா சார்? அங்கேயே இஸ் ஈக்குவல் டு 0ன்னு போட்டு முடிச்சிடலாமே சார்?
இல்ல இது வந்து ஆர் ஆஃப் எக்ஸ் வந்து காமன் டேர்ம். ஒவ்வொரு மெத்தடுக்கும் இது வந்து எப்ப ஈக்குவேட் பண்ணுன்றது இருக்கு. இந்த பாயிண்ட் கலோகேஷன்ல டைரக்டா ஆர் ஆஃப் எக்ஸ் ஜீரோ, சப்டொமைன் வரும்போது இன்டெகிரல் ஆர் ஆஃப் எக்ஸ் ஜீரோ, அந்த மாதிரி மாறிக்கிட்டே வரும். ஸோ அதனாலதான் இதை காமனா வச்சுக்கிட்டேன். ஓகே, ரெசிடுவல் ஆர் ஆஃப் எக்ஸ்ன்றது ரெசிடுவல்னா எரர். எப்ப நமக்கு எரர் ஜீரோ ஆகுதோ அப்பதான் வந்து நமக்கு வந்து சொல்யூஷன் வந்து எக்ஸாக்ட் சொல்யூஷன் வரும், ரைட்? இந்த இந்த எரரை ஜீரோ பண்றதுக்கு ஒரு 4 மெத்தட். அந்த மெத்தட் தான் பாயிண்ட் கலோகேஷன், சப்டொமைன் அந்த இது. ஃபர்ஸ்ட் மெத்தட் என்னன்னா அந்த பர்டிகுலர் மிட் பாயிண்ட்ல ஜீரோன்னு சொல்றோம். எரரே இல்ல, மிட் பாயிண்ட்ல எரர் இல்ல அப்படின்னு சொல்றோம், ரைட்? அப்போ வந்து என்ன பண்றோம், மிட் பாயிண்ட் போது 0 to 500 மிட் பாயிண்ட் வந்து 250, 250ல எரர் இல்ல அப்படின்னு சொல்றோம். அதுதான் ஆர் ஆஃப் எக்ஸ் இஸ் ஈக்குவல் டு 0 அப்படின்னு போடுறோம். Can
ஓகே
able to get
சார்.
it?
எஸ் சார்.
Okay. Right. So the next one is subdomain collocation. So according to subdomain collocation, integral r of x dx is equal to 0. Okay. In the integral limit வந்து என்ன? So the limit depends on the cantilever bar. So the bar starts from 0 and ends at 500. So my limit is from 0 to 500. R of x dx is equal to 0, which means integral 0 to 500. What is this R of x? R of x is 2ae a2. 2ae a2 dx is equal to 0. Okay. So let me integrate this. So when I integrate, what will get? I'll get 2ae a2. Integrating dx, you will get x. Limit is 0 to 500. Okay. This is equal to 0. Right. I am equating this to 0. In that case, whatever you apply anyway, so that will go again. I can say that a2 is equal to 0. There is no change in your method. So you will get the same value as point collocation. In that case, again, your u of x, the same value. There is no change in the value. So you can able to see that. So this is my value, right? So you consider the same thing. I will substitute a2 as 0 here also. So I'll getting the same value 0.0011. Okay, so this is my subdomain collocation, right? So you will get more accurate when you have more constants. I am taking only one constant, right? So a2 மட்டும் தான் எடுத்திருக்கேன். இதுவே வந்து இந்த ட்ரையல் ஃபங்க்ஷன் வந்து plus a3x cube அப்படி எடுத்தனா இங்க ரெண்டு கான்ஸ்டன்ட் வரும். அது வந்து காம்ப்ளிகேட் ஆயிட்டு போய்டும். So it takes lots of time. அதனால தான் I reduced it. Okay, so I consider, so depends on the question. Okay, questionல எதுவுமே கொடுக்கலனா இதோட நிறுத்திக்கிட்டா கூட போதும். So don't waste your time in including one more. Okay, if they didn't mention anything in the question, don't go beyond this. You stop up to this, that is enough, right? Okay, so let me go for the next method. My third method is least square method, right? In least square method, what we say, we'll get integral 0 to 500. We'll call w1 r of x dx is equal to 0. We'll include w1, a weighted function. What is this w1? W1 is partially differentiating your r of x with respect to the constant. So what is the constant we have? We have a constant a2. right? So I am partially differentiating with respect to A2, and I will be multiplying with R of X, and I will integrate it. Okay, this is the least square method. So let me identify what is W1 then. So W1 is dou by dou A2. So what is your R of X? R of X is 2AE A2, right? So when I partially differentiate this, I will get 2AE. Okay, so what I'll get? I'll get only 2AE. So again, I think there is no change in the answer. Okay, so again, when I integrate, integral 0 to 500, W1 is 2AE, X is equal to 0. So you know that this 2AE is a constant. When you bring it on the other side, that becomes 0. So in that case, I can rewrite it like this. Integral 0 to 500 R of X dx is equal to 0. I can write it like this. Because this 2AE is a constant. Bringing on the other side, that becomes 0. So you have only this term. Okay. So this is nothing but what we solved previously. So subdomain. Same. Integral 0 to 500 R of X dx is equal to 0. That is what we identified, right? In that case, there is no change in this least square also. Okay. So I think all are same here also. So I'm not going to repeat it again. So last method, right? So fourth method is Galerkin method, right? So what will say? We will say integral 0 to 500 W1 R of X is equal to dx is equal to 0. But what is this W1? W1 is dou u by dou A2, right? So W1 is dou u by dou A2. So you can able to see that. So previously dou R, least square is dou R, whereas here it is dou u. So in that case, let me identify dou by dou A2. So what is my u value? This is my value, right? So I have to partially differentiate these things. Okay, so this I have to partially differentiate it. So here A2 is the variable, others are constant, right? So you eliminate that. So in that case, what will get? So here I will get minus 1000. So because A2, it is, you consider this as A2 as X, which means it will become 1. So remaining term is minus 1000 X. So I'll get minus 1000 X in, for this plus X square, right? Plus X square. Okay. So this is my W1. My W1 is X square minus 1000 X. Okay. So now what I do, I will be partially integrating this 0 to 500. My W1, I will enter it here. So X square minus 1000 X. R of X, R of X is same. So what is my R of X? 2AE A2. So 2AE A2 dx is equal to 0. So now multiply this. So this 2AE A2 is a common term, right? So I have no need to multiply. So just directly I will integrate it. So when I integrate, what will get? So I will get x cube by 3 minus 1000 x square by 2. My limit is from 0 to 500 into 2AE A2 is equal to 0. Right? This is my term. Right? Okay, you can able to understand. So integrating the x square will be x cube by 3, and sorry, I missed one 0 here. So minus 1000 x integrating it x square by 2. So limit is 0 to 500. Okay. So the remaining term. So when I expand it, so what I'll get? I will get 500 cube divided by 3 minus this will be uh, when I cancel this, you will get 500 here into again 500 square. Okay. So this term into 2AE A2 is equal to 0. Hope, I think you can bring the all the terms here. Again, you will get A2 as 0. I think there is no change. Okay, so which means you will get the same answer. There is no difference there. So in all these three methods, we are getting the same answer because we have taken only one unknown. Okay, if we take two unknowns, you can surely see the difference, right? So you can surely see what is the difference with respect to this. Okay, so when I substitute everything, we are getting it. Why we are getting 1 1? Because it is approximation. It is not accurate. Okay, so all finite element itself is an approximation method. Okay, so which means I will get only approximate answer. I won't get the real answer. You can't conclude that this is your final answer or the exact solution. Okay, so let me consider same cantilever bar which is having a self weight. So assume that this beam is kept in vertical way so that weight is acting on it. Okay, so that is a uniformly distributed load. So what you will do, you apply a boundary condition. My boundary condition is when x is equal to 0, u is equal to 0, and when x is equal to L, your u is not equal to 0, but I have to apply something. So I will apply what is my force. My force again at that point is 0. So there is no force mentioned. Previously point load இருந்தது, அதனால we mentioned a point load. AE du by dx is equal to that point load. We mentioned it. Whereas in this case, there is no point load. It is purely self-weight. Okay. So which means your F is equal to 0. Okay. So what you will do, I will write it like this. AE du by dx at x is equal to L is equal to 0. Okay. So I know what is the differential equation here. So that is what AE d square u by dx square plus q, where q is here, which is the UDL, right? It's a varying uniformly distributed load. So where q we mentioned as a into x, right? It means at a particular location you have to multiply with x. X is my length. Okay, so this is what self weight is, right? So let me consider. So I think there will be a little bit confusion here. So I will tell you what is it. So let me take here. So I will keeping this vertical, right? You have a self weight here. Let me consider this self weight is 10 Newton per meter. Okay. So here x is equal to 0 and here is x is equal to some 100 mm. So what it means is this a into x. What it means is, so when I take this length, when I take x is equal to 5, right? My weight will be 10 into 5, which is 50, right? Up to this, it is 50, right? That is what, this is A, this is what we mentioned as A, and this is X. So when I take at this location, which is, let me consider 75. In that case, my weight will be increased. So 75 into 10, which is 750. Okay, so your weight is increasing with respect to your distance. Okay, so whenever I take a particular point, you have to multiply with your x term, which is the length. So that is what we called as a into x. Okay, which is purely related to self weight. Okay, so you have this. So I am writing it as an equation. What is my equation? AE d square u by dx square plus ax is equal to 0. So this purely depends on UDL. If there is no UDL, this will become 0. Like this is what we solved in previous problem, right? We consider AE d square u by dx square is equal to 0, right? So same thing. So, but if you have UDL, you will consider this also, which is A into X. Okay. So now let us consider this. I'm going to apply a tail function. Okay. What is my tail function? Let me call it as U cap. So this is a derivation. So kindly note what is the notation here. So previously I called something called as U. Now I call something called as U cap, right? So U means your original, your exact solution. U cap is trial function. U cap is trial function. You consider a trial function which is satisfying your boundary conditions. Okay. So what I do is I substitute this tail function in my differential equation. What is my differential equation? AE d square u by dx square plus ax is equal to 0. This is my differential equation. If I substitute this tail function here, I'm making this as u cap, as I shown here. What happens? When I substitute my tail function, it is not equal to 0. Right? Because I say something as some value, I say that is your answer. Surely you will get an error, right? That error we call it as your R of x. So this is my R of x. Okay. After I am substituting, I am getting this R of x. Okay. Now I am going to use this Galerkin method. So according to Galerkin method, so what do you have? So integral weighted function w of x r of x is equal to 0. This is my method, Galerkin method. So what is this w? W is dou u by dou a. So where a is your unknown values, right? So, but anyway, so let me call it as w1, wx. What is this r of x? Let me substitute this r of x. Ae d square u cap divided by dx square plus ax dx is equal to 0. So multiplying this, I am getting like integral 0 to L wx ae, this one was one term, plus integral 0 to L wx ax dx is equal to 0. This is another term. Okay. Now what I'll do is I'm going to integrate it. Is it possible for you to integrate this one, this term? How to integrate this one? Is there any way?
UV method, integral u v
Yeah, very
dx.
good. Yeah, very good. That is what I expected. So UV method. So integral by parts, right? So you have a differential equation and some another equation. So in terms of x and other things. So in that case, if I want to integrate this thing, what I have to do is I have to use integral by parts method. So by parts is UV, right? So what I do, I'll use, this is my formula for that integration. Integral u dv is equal to uv minus integral v du, right? This is my formula, right? So what I consider u as w of x and dv as ae d square u cap by dx square. So what are the terms I required? I need required v and du, right? U is already here and dv is here. Okay, so if I want v, right? If I want v, what I have to do? I have to integrate this once, right? I have to integrate this once, right? If I want du, I have to differentiate this once. Okay, so let me put. So in a differentiate this, what I'll get du is equal to dw by dx into dx. It is some constant. I am having something like this, dw by dx into dx. V, if I integrate it, we'll get integral ae d square. So this will be ae d u cap by dx. So one differentiation will go off, right? We'll get ae du by dx. Okay. So now let me substitute it in my equation. When I substitute, I'll get something like this. So u is w of x, v. So v is this term. So you have it here. So ae du cap by dx. So this is over, right? So I can apply my limit 0 to L. Okay, minus integral 0 to L, right? AE du by dx. What is this AE du by V? V is AE du by dx. So the same term is applied here, right? Into du. Du is this. So you have it here. Okay, this is my du. So I'm substituting. I'm getting some equation, something like this, right? So we already discussed what is AE du by dx. What is AE du by dx? So we call this as force, right? So this entire term indicates what is the force, right? So the entire term is force. Okay. So now what I can do, I'll write the equation like this. So after applying my limit, force at x is equal to L, force at x is equal to 0, and I'll get this is my overall equation, right? So this equation we call it as weak form. This we call it as weak form. Okay. So maybe they will ask this for 16 mark, this derivation. Okay. So what is the purpose of Galerkin method? So Galerkin method will make your differential equation weak. Okay. What it means? So it means that, so if you have d square u by dx square, right? You know that you need u is equal to a naught plus a1x plus a2x square. But after making this, so it is weakened. Your differential equation is weakened like this. So what is the maximum power here? It is power 1. It is power 1. Big, in that case, you no need to use this tail function, this much amount of tail function. You can use just a naught plus a1x. That is enough. This tail function is enough for this equation. Whereas for this equation, you require a tail function up to x square, right? So after you apply Galerkin method, it weakens your differential equation, which reduces your tail function, right? So because all are power 1, so this is enough to solve your problem, right? So there comes your element. So when I say element, it means it is having two nodes. So node number 1, node number 2, which is connected by a line. So this one is an element. So because this is linear, so you can able to get a linear line, right, as an element. So if you use this, what happens? Your element will be like this. Somewhat complicated, right? Your element is complicated. Okay, what are the other importance? So it is a second order, so that's what I'm indicating. So it is a second order equation. So minimum trial function required is up to this. Whereas this is a first order equation, the minimum trial function is just a naught plus a1x. This is the first one. Second, if you have this trial function, you need at least two boundary conditions, right? So one we call it as an essential boundary condition, other one is a natural boundary condition. Okay, essential boundary condition is without any derivatives. When x is equal to 0, u is equal to 0. When x is equal to L, u is equal to 0. So these are all we call it as a essential boundary conditions. There is no derivative in your boundary condition. Okay, non-essential is it is having a derivative. So usually what is this cantilever bar? We call it as a du by dx is equal to 0, right? So instead of u, we call it as du by dx, derivative of u, right? So that is non-essential or natural boundary condition, right? So in this particular equation, you require both equation, boundary conditions. ரெண்டு boundary condition apply பண்ணாதான் உங்களால solve பண்ண முடியும், right? So most of the time இந்த boundary condition கஷ்டம் கண்டுபிடிக்கிறது, right? So some little bit complicated இருக்கும், right? Whereas now after you weaken this, only one boundary condition is enough, which is your essential boundary condition, right? You can easily solve any problem using this weakened differential equation, right? So this made to derive a matrix. We call this as a element stiffness matrix. Okay, so we will derive these things in next unit, right? Not now. So next unit we will derive it. So I will show how to derive using this weak form. So that gives you an element matrix which will be used. Okay, so today we will stop here. We will continue in next class.